Thank you all for being here. Hi, everyone, and thanks to the organizer for giving me the opportunity to present my work. Now, my first ever talk was actually in primary school at the age of 8 about my favorite animal, the koala. So I'm very happy to be in the land of the koala, but this time I won't be talking about the cute creature, but about the chemistry in the disk around L2 Puppis. So I think by now it's quite clear that AGB outflows that are, well, generally not spherically symmetric. These spherically symmetric outflows appear to be the exception rather than the rule. And this postcard of the ALMA large program atomium is a nice example of this asymmetry. So here you have 12 oxygen-rich AGB outflows, and none of them are spherically symmetric. Some a bit more so than others, but generally they're all a bit of a mess. And we think that these large-scale asymmetries are caused by binary interaction, so either with a stellar companion or a planetary companion. But when it comes to modeling these outflows, especially when it comes to chemical modeling of the outflows, we still assume spherical symmetry. So if you have this one-dimensional representation of an outflow, you have chemical models that are geared towards the non-equilibrium chemistry in the inner wind caused by shocks due to the stellar pulsations. And then you have chemical kinetics models that are geared towards the photochemistry of the outer regions, and you can extend them inwards to include dust-gas interactions as well. But all of these models are one-dimensional, which means that they are inherently spherically symmetric. Now, you can make some tweaks to sort of take spherical asymmetries into account. You can, for example, introduce clumpiness, either by using a porosity formalism or a different parametrization. And you can also take the effects into account of a close-by stellar companion. So you can do quite a bit of things with a one-dimensional model, but these are all still sort of like fudge factors, attempts to to have a one-dimensional approximation of a three-dimensional problem. And it works quite well, but if you have specific structures, a one-dimensional model is not going to work that great. This is a sphere observation of L2 Puppis, and here you have a dark band, which is a dusty disk, and you have these two cones of light, which is light that's being scattered off the dusty disk. And L2 Puppis is an oxygen-rich AGB star, and it's quite close. It's at a distance of 64 parsec, making it the second closest AGB star. And that's also why we can have such a nice image of the dusty disk surrounding this AGB star. Very edge-on, as you can see. Now, we also have ALMA data, and if we add this to the observations, you see that there's a red blob. The blob also moves around over time. And this red blob is a tentative planet detection, about like a few Jupiter masses in size. And these planets could be the reason behind the disk. There's some modeling about that. It could also be a completely different forming mechanism behind the disk. We don't know how the disk is formed, but we do know that it's there. And if you then are a bit more chemically inclined, like I am, you might wonder whether there's any chemical signatures of such a disk. And for this, we will need to develop a new model, because a one-dimensional model is clearly not suited for this environment. And when creating such an AGB disk model, why not start with modeling this well-observed disk around L2 Puppis? So that's what I, with my co-authors, did a while ago. We did it for a long while, and our results have recently been published in the monthly notices. I'd like to highlight one collaborator in specific, namely Catherine Walsh, who is an expert in the chemistry of protoplanetary disks. So there's a bit of overlap between young disks and very old disks, well, around old stars at least. So first of all, we had to extract a new physical model of the disk around L2 Puppis. For that, we used archival data. So we used ALMA observations of 12 CO and 13 CO. These are the moment zero maps of the 3-2 lines that we used. And you can again see it's quite a nice disky structure. And we then fitted a widely used parametrization for protoplanetary disks to the data with a lot of trial and error using a 3D radiative transfer code called Magritte, which is publicly available. So after a while, we finally got this structure for the disk. So at the top, you have the density, and at the bottom, you have the temperature. So it's quite a small disk, about 10 AU in height, and some 15 AU radially. It's small, but not too small compared to protoplanetary disks, but it's especially very warm. So you have quite large temperatures of more than 1,000 Kelvin in the inner regions, and our midplane stays quite warm, so 700 Kelvin at least throughout our entire disk. So that's very different compared to a protoplanetary disk. We then fed this new physical structure into a disk chemical model that was used for protoplanetary disks before, feeding it oxygen-rich parent species, and then we just let the disk do its thing. And here you have the evolution of CO over time. So we have output after 1,000 years, 10,000, 100,000, 500,000, and then finally 1,000,000 years. So we have the abundance of CO, and it shrinks a bit in size because of photodissociation, but it still looks very much like a disk, which is great. And it also looks quite a lot like the observation. So yay, sanity check. And if you then look at the other parent species, SO, it's an oxygen-rich parent, it's an oxygen-rich disk, so SO is a parent. You see that after 500,000 years, a gap starts to appear within the midplane of the disk. Now, SO was previously observed as well at a spatial resolution that would have been high enough to resolve this gap if it would have been there. And we don't see this gap within the observations. So using the chemical model, we can tentatively age the disk at being not much older than 100,000 years. Now, this is, of course, assuming that our model is correct. And one of the big assumptions that we make is that the disk is static. So this means that we feed it, we give it structure, we give it some parent species, and then it's only the chemistry that is evolving. So there's no significant contribution of new outflow material to the disk. But if we assume that that's an okay assumption, then we can sort of use chemistry to age the disk at about 100,000 years. Right, let's take a look at some other molecules, and I'll show results for 100,000 years. So here you have water, a parent, so it's nice disc-shaped. And then you have OH, which is a daughter species of water. So it's formed by UV photodissociation of water, and it's only present in the outer edges, which is what you expect, because that's where you've got quite a lot of UV radiation, so your water can be broken up. It's the equivalent of having a shell-like structure for your daughters in an outflow. So some things behave quite nicely, as you would expect, but other things are, all molecules are quite surprising. For example, the formation of complex organic molecules within your disk midplane. So you can have quite high abundances of, for example, methanol, CH3CN, and some longer complex organic molecules as well. And here I show you the column density of the complex organic molecules as found in the disk compared to the column density that they would have in a low-density oxygen-rich outflow, so the surrounding outflow of L2 Puppis. So those are the crosses. You can see that the column density can increase quite a bit. Well, it does increase for these clumps quite a bit, and we find that some of the complex organic molecules actually become observable. So that would be nice to check later on. And these complex organic molecules are formed via cosmic ray-induced chemistry in the disk midplane. The midplane is well shielded against UV photons from the interstellar radiation field, but cosmic rays can still wiggle their way through, reach the inner disk, the inner midplane, and break up carbon monoxide, liberating carbon, which then goes on to a journey to become a complex organic molecule, for example. So lots of things happening in the midplane, but also if you look at the outer edges of the disk, you find some carbon-bearing species that are very abundantly present. So you have C2H2, C2N, SiC2. That's like carbon-bearing molecules. You wouldn't really expect that an oxygen-rich outflow or disk maybe has them, well, has these species at such high abundance. And in this case, we find that these molecules are formed through UV-driven photochemistry in the outer regions. So the midplane is where all the cosmic rays can do their thing. And in the outer regions, you have lots of UV-induced photochemistry leading to carbon-bearing species, carbon-bearing molecules. In fact, there's quite a lot of carbon chains that can be formed. And if you then add up all of your carbon chains, so everything with at least 6 carbon atoms or more, we've added it all up in a sync particle. You see that the abundance can be very high, well, quite high, in the outer region, so more than 10 to the -5 with respect to H2. So that's a lot of carbon floating around in your oxygen-rich disk. So that's quite interesting. And this figure summarizes a bit what I've been talking about. So it shows you, on the left, you have species that show a decrease in column density with respect to an outflow. So for example, CO2, its column density can decrease by about 5 orders of magnitude. But if you look at CN, at HS, NH, so species that are, well, observable, maybe not at HS, its column density decreases about 2 to 1 order of magnitude. And here on the right are all the species that show an increase in column density within the disk. I'd like to point out HC3N, so that's 6 to 9 orders of magnitude more that's floating around, but then all the species are like from 2 to 4 orders of magnitude, such as SiC2 that I showed previously. So your disk, the physical structure of the disk, really has a large impact on chemistry, and these molecules could be used as a tracer, as a tool to trace disks, because not all disks are as easily or as nicely resolved as a disk around L2 Puppis, because, well, that's really close by. All the other ones are a bit further away. So chemistry can lend a hand in discovering these disk-like structures. So we've now resubmitted an ALMA proposal to observe some further density and temperature probes to really pin down the physical structure of our disk, since, well, it has such a large impact on the chemistry, and maybe a slight variation can lead to different results. And of course, to test our model predictions, because we predict that, for example, comms are there and other molecules as well. And by doing so, we can test our model assumptions. So is the assumption of a static disk okay? Or is there actually still a significant amount of material that's being fed into, like, through the disk or onto the disk? So that will be quite interesting to take a look at. And hopefully this time we get some data. That will be great. So I'll end here with my conclusions. We have updated the physical structure of the disk around L2 Puppis using a protoplanetary disk parametrization. And we used this to develop the first chemical model of a disk around an AGB star. And we find that the physical structure of a disk has a large impact on its chemistry. So there's quite a lot of carbon-bearing molecules floating around, including the formation of complex organic molecules. And using the model, we can tentatively age the disk at about 100,000 years. Now, I mentioned before, this is a static model. We just assume that the disk is there. If you really want to take a look at its evolution and its chemical evolution, you would need a hydrochemical model. And in order to develop this, you would need to do some computational tricks that Silke Maas will talk about a bit more tomorrow. And with that, I'd like to thank you for your attention.
Hi, thank you. It's super interesting work. I have a few questions, but I'll start with one and then we'll see. Where is the inner disk radius? And do you know that from observations or not? Yeah. And is the companion like in between? Or?
Yes, so the inner disk radius is at 2 AU and the companion is also at 2 AU. So from observations, the gas starts at 2 AU and then you've got the dusty disk that starts at 6 AU. That's so the gas you know from ALMA, the dust you know from SPHERE, and also the location of the companion is also at 2 AU from ALMA. So it's the companion is really within the, well, yeah, you've got your companion and then your disk starts.
Okay.
Right.
I would like to know, you said it is a static model, right?
Sorry?
You're using a static model.
Yes, it's a static model.
So how do you implement the chemistry in your model?
So I assume oxygen-rich parent species and with a specific abundance throughout the entire disk in the start point, and then I let it evolve. So if I go all the way back here, you see that, so at the beginning, there's like an equal amount of CO, well, relative to H2, but then the chemistry takes place and you sort of equalize into a disk structure. So in the beginning...
So what is the equilibrium you are looking at? Is a photoionization equilibrium?
Sorry?
What you're going to you are evolving the system to something.
Yeah.
An equilibrium, right? Are you?
Yeah, I suppose you could evolve this to equilibrium, but I cut it off at 1 million years because that's the average lifetime of an AGB outflow. So, I mean, you could go further, but it's doesn't really mean anything because the AGB.
So you're not looking in from the perspective of a physical time scale, or I mean, you can evolve the system to to attain a photoequilibrium or something like that.
Yeah, that's a great question. I haven't really thought about it, but I think you could. Yeah, it's like a disk. It doesn't. Yeah, after a while, it should reach a certain equilibrium stage.
Okay.
That's something that I could look into. Yeah.
So you see that in your evolution, that there's a point where nothing is changing.
So I stopped the calculations after 1 million years to keep it physically reasonable. But if you look at this, sorry for the flashing, there you go. So you do see that the column densities just change over time. So perhaps this would like flatten off, like this evolution would stop after maybe a few more million years, but I haven't looked into that. But yeah, that would be something to look into. Thanks.
Okay, thank you so much.
Thank you.
Yes, a nice talk, Marie. I have a question about I mean, you mentioned that you plan to test all this carbon richness with ALMA. Have you thought whether it could be use also the James Webb?
Yeah, that would be very nice.
Okay, and
I'm going to talk to some people at Leiden who are like really, I don't know much about observations, let alone the JWST, because maybe it's too bright because it's so close by.
Yeah.
But then the JWST has a coronagraph. Maybe you could like look away. I don't know.
Okay.
That would be great.
And which molecules do you think could be a good test? I mean, methane or acetylene?
So yeah, definitely we're going to try to look at methanol because there have been some, well, methanol was already covered by previous observations, but it wasn't detected. But that could be due to the different temperature structure as well. So we did do some modeling a little bit. So I think we were looking at SiC2 as well, because it's a quite high abundance, HC3N, because those are also HC3N and some, no, of course, I'm blanking on the proposal, but some of these molecules are also commonly used as temperature probes in a protoplanetary disk. So it's like a 2-for-1. Yeah, like definitely looking at some of the comps, whether they're actually there or not.
Okay.
Yeah.
Thanks.
JWST would be great.
Thank you.
So maybe this is a naive question, but L2 Puppis is a very well-known semi-regular variable as well, right? Do you think you're including, is there any way that pulsations would play into this disk, or do you think you would need to do that, and what maybe would change if you did?
I don't go into why the disk is there. But there has been a hydro model from Chen in 2016 who tried to recreate the disk, well, knowing that there's a companion there, and they needed actually to just have the star just had to have gone through a thermal pulse, and then the binary companion could really capture it all and make it into a disk. So there's a lot of tweaking. But yeah, the pulsations, I think that's also what Joachim showed earlier. So you've got this star like throwing dust all around. Yeah, there's a lot going on within the first two AU, but then we've got our nice disk. And that's when I'm a simple woman. I can't take everything into account. But yeah, that's a great comment. And there's probably an interplay there.